This one, right?
Yes, sir.
Okay. So this is what basically, this is a universal curve. Last time we were discussing about charging and discharging of the capacitor, how it charge, how discharge basically. So charging is not like, you know, it quickly or suddenly it's charged. It charge basically exponentially. So the red graph which you can see here, the red one is showing here that, you know, basically this red one, this is the charging curve. Yani capacitor is charging exponentially. The voltage across it developing exponentially. So it's showing here the points which are important here, which you can see. And what is the tau here? This tau, you know this tau, na? Tau is what? A time constant. And what is its value in RC circuit? Tau is defined as, tau is equal to R into C. Getting point? So this is what? R into C. So now, and what is the unit of this tau? Because this is a time constant, so the unit is second basically. Okay, so your resistance must be in ohm, your capacitor must be in farad, so you will be getting tau in second because it's a time constant. So according to the time constant, we can see at one time constant, capacitor will charge 63% of its final value. Yani if you are applying 10 volts to the capacitor, so it will reach up to 6.3 volts in one time constant. It is like that. Now two time constant, yani it will reach to 86%, or you can say 8.6 volts if the final voltage or the source is 10 volts. Similarly 3, 4, 5, and the 5 time constant we called it reached to 99%. Yani we called that almost capacitor will charge 100% at 5 time constant, because 99 is almost 100 considered. So, or exactly 9.9 volts we can say. So whatever I just explained to you for the charging curve, which is the red one, now is exactly opposite is applicable for the discharging curve. So blue one is the discharging curve, which is saying that at one time constant, capacitor will discharge, okay, 37%. Yani whatever its value, it will discharge to 37%. So how can you know this value? You already know the charging. So if you just simply subtract 100 minus charging, which is 63%, okay, at one time constant, you will simply get 37%. You know, this is something. Similarly, 86. So 100 minus 86 will give you 14. 95 will give you 5 if you subtract 95 from 100. So this is the way. So this is a universal curve. So from that curve, we can easily get it in how much time the capacitor will be charged to which value basically. So this is a universal curve basically. So it is again drawn between, you can see the number of time constant on x-axis, on y-axis, the percentage of final value. All right. So this is universal curve. See now, so this universal curve, now it is drawn separately for charging and separately for discharging. See, so this is what charging, you can see left one, it is for the charging curve, which is rising exponential. And this is what, this one you can see, this is falling exponential, this one, okay, decreasing exponential. So this is charging, this is discharging. Now, 5 time constant interval is generally accepted as the final to the fully charged discharge capacitor, and it is called transit time. So this time when a capacitor will charge or discharge, we call transit time, and it is equal to how much? 5 tau, 5 time constant. So in this time, capacitor will fully charge and fully discharge, and the value of tau, you know that it depends upon RC. Okay, how much you value set, R or C. So accordingly, it will charge and discharge. Okay, now, so see this one, the equation, which is basically the instantaneous equation for the charging and discharging. Means by knowing this equation, we can find at any time, how much capacitor will charge to its final value. So here are some acronyms for that. This is VF, which is telling you this is final value. Similarly, VI, initial value. Okay. Similarly, we have what? VF. Then e raised to power minus t over RC. Do you know what is RC? RC, time constant. Like I just explained, this is what it is equal to tau, time constant. So this is an instantaneous equations. By knowing this one, we can find the capacitor value at any instant of time. So now we can break these equations two ways. Yani we can say charging equation. Similarly, we can say discharging equation. So for the charging equation, girls, for the charging, you see that the formula for the charging basically. So when the capacitor is charging, okay, so what we consider that the initial value, yani the capacitor is fully discharged. So when full capacitor is fully charged, what will discharge? What will be the initial value? Initial value, if the capacitor is discharged, voltage across zero. Yeah, so if we put Vi is equal to 0 in this equation, girls, so you will see Vf plus 0 minus Vf, and Vf will be common here. So we can take Vf common, so inside will be having 1 minus e raised to power minus t over Rc. So this is, just what you call reduced form of the same. Okay, even if you remember that one, it is sufficient rather than just, memorizing two different equations. So it's up to you. Now, similarly for discharging. Now, girls, for the discharging, when the capacitor is discharging, what will be the final value for the capacitor when it is discharging?
0.
You know that, yeah, it's going to be 0, because when we are discharging the capacitor, so the final value which it can hold, that is going to be 0. So if we put Vf is equal to 0 in this equation, see, when you make it 0, so what will remain? Only Vi multiplied by this one. So this is that one. Getting the point? So these two equations is basically the simplified version, or you can say special cases when we are considering only charging, when we are considering only discharging. Even you can just use this equation and put the values according to the condition. So let's see a question to understand this thing. So see this question. First, try to write what is given to you, then you know the rest of the things. So what are the things which is given to you when you read what is given thing?
The capacitor voltage.
Capacitor voltage. Okay, determine the capacitor voltage. It's not given to you. It is asking you determine.
We have RC, so we can find the time constant.
Okay, yes, we can find the time constant, correct? So time constant is RC, and how much is R? This is 8.2 10 raised to power plus 3 multiplied by C, which is 0.01 micro 10 raised to power minus 6. Okay, get it? How much you are getting?
It's going to be 82 microsecond.
82 microsecond. Micro or milli? Micro.
No,
Micro. Okay. So this is tau. We got it from here. All right. One thing. Now, what is given to you? If you look, so this is what they are asking you: how much this capacitor will charge? Okay, in 50 microsecond. What is given? Time. Understand? And we want to know in 50 microsecond how much this capacitor will charge. So T is given. Now, other than this, what they are saying. So initially the switch is open. You can see this is the switch. Okay, it is open. Yani no current is flowing. So when the switch is open, so even see one condition is given to you. The capacitor is initially
uncharged.
Uncharged. Yani
Vi equals 0.
Vi equals 0. Yeah, it is also given to you. Right. Now, can you tell me when I close this switch, okay, what will be the final value the capacitor can charge? Vf. Yes, correct. It is maximum value that it can charge. It is the 50. Yani the source which we are applying here, it can charge maximum. So these are the things which is given to me. Now time to apply the equation. Instantaneous equation. V is equal to Vf plus Vi minus Vf e raised to power minus T over tau or T over RC. That is same thing. Okay. Now, so we know that Vi is 0. So if I put Vi 0 in this equation, so this equation will become Vf 1 minus Vf, no,
1 minus e to the power 50. Right.
T over tau, this one, correct? This will be the equation when we put Vi is equal to 0. So this is something. Now just put the values. So Vf is 50. We know that 50 volts. Now inside 1 minus e raised to power minus T, which is given to you. How much? 50 over 82. By the way, both unit is same. Both are micro. Correct or not?
Yes, correct.
Yeah, this is important. Then it's better if you just keep tau and T, unit same, so that because it's a ratio, it will cancel out. Bas, khalas. Now use your calculator and find.
It's going to be 22.8 volts.
22.8 volts. Khalas, very good. So now idea is clear. What you get it? What this value is telling you? This value is telling you that the capacitor in 50 microsecond will charge up to 22.8 volts. Is it clear now? Understand?
Yes, clear.
Okay. Now, if I just ask you a simple question, girls, can you tell me in how much time this capacitor will fully charge? Five tau. Very good. Yes. So fully charged is equal to 5 tau. Okay. And 5 tau we already know 82. If you multiply 82, I think 410 microsecond. It means is that yani in 410 microsecond the capacitor will be fully charged. All right. Now, if I ask girls, can you draw the curve, charging curve? So yes, it's so easy because you know that it is going to be rising exponential. So I can draw like that. Here I will say time. Here I will say voltage. And I can draw, it is gonna be something like that. Okay, curve is always same. Now rest thing I can simply draw like this, dot dot dot, and some values I can give here. So even if you want to know all values, 1 tau, 2 tau, you can easily get it. How can you get it? Just simply yani 1 tau. 1 tau, it will be how much it is? 82 microsecond. And 2 tau will be is double yani something like that. So I can just mention this is 1 tau, this is 5 tau, and some way you can this way you can draw that one. It is there already. I will show you. So if they say last one, draw the charging curve. So yes, you can also draw that one. See this one. So this is the charging curve which you can see here. Okay, which shape is always rising exponential. And now this is 1 tau, this is 5 tau. Okay, and because you know that this is tau and the time which is 50 is that 50 is basically less than the 82 yani which is what? Tau. Okay, so less yani it definitely it is gonna be somewhere below this 150. So it is saying 22.8% will charge. And now in 5 time constant, it will charge maximum 50. So this is the curve which you can also draw. Some lines you can draw. Clear? All right. So
Yes.
this type of questions are possible from this, and inshallah with the time this course is gonna be now interesting with if concepts are clear, so you will understand basic things, yani how charging, how discharging, when we close the switch what will happen. See now next. So again one more question, and this time we have no battery in the circuit, but in place of battery we have given a capacitor which is gonna behave like a battery, temporary battery. So now question is determine the capacitor voltage. Again they are asking capacitor voltage, and what they said, at a point in time 6 millisecond after switch is closed. So you see here we don't have any battery, we have only capacitor and we have resistance. So when I close this switch, what will happen? This capacitor will discharge via this resistance, because resistance will consume the energy. So it will discharge. Okay, have you seen the capacitor, girls? Any one of you ever seen the capacitor? No. Okay.
You mean how does it look like?
Yeah. Okay. Okay. So I have a capacitor, and I have a capacitor. I'll show you. I'll turn on my camera and I'll show you. I have with me. Then I'll show you how it is charged, how it is discharged. All right. So I think no problem to open my camera, right?
Yes, of course.
All right. So where is this? Okay, at least you can see your teacher also. All right. So this is a capacitor. Look here. I'm bringing close to you. There are different kind. This is one kind. It is called electrolytic capacitor. Can you see?
Yes.
Okay.
Yes.
See it has two legs. One is short, one is long. You can see. All right. So the long one is positive. The short one is negative. Even it is mentioned there. If I bring close to you, you can see the minus sign, right?
Yes, we can.
Yeah. So this is negative, right? This is short leg. And another one is positive. Now, this is what kind of electrolytic capacitor. Electrostatic capacitor. There are different kind. Another type ceramic capacitor is like a very fine thin layer of it. Now see the value is also mentioned. I don't know. Can you see his Philip value or straight? 18 volts. Can you?
Yes. 16.
Yeah. 16 volts. Okay. Yes, 16 volts, and its value you can also see 4700 micro.
Right. Yeah.
Okay, so this is a capacitor basically. Now, and everyone knows this one, the battery. Do you know this battery? Maybe you use somewhere in component, or this is 9-volt battery. All right. 9-volt battery. Yeah, even it will be mentioned somewhere. I can show you this one. Okay, so see, this is the negative here mentioned. So negative terminal of the battery. This is another one is positive terminal. So what is negative? This is negative, and a big one. Okay, and this is the positive. And this is DC source. You know that one, DC source. Okay, what next? This is LED, light emitting diode. LED stand for light emitting diode. So it's you will next is gonna be what you will study. This is basically PN junction diode and all. So it's made up of it. So it is like that. All right. Now let's see. So as I explained to you, this is 9-volt battery, and this is what a capacitor. And as you know that a capacitor can store energy, but it is gonna be temporary, right? So see, for example, if I connect this LED to this capacitor, okay, so it will not glow because it is initially uncharged. Getting point? So I'm going to connect this one. So positive with the positive of this capacitor. Can you see this back side or clear or not? See this?
Yes, it's clear.
The long one and the short one. So I'm going to connect this way, right? So long to long, short to short, any positive, positive, negative to negative. See, I did just touch these. Can you see it's glowing or not? It's not glowing.
No, it's
No. All right. So what I'm going to do now, I am going to charge this capacitor. So this is a battery. I will connect this battery with this capacitor. So capacitor will hold the charge, okay? And it can hold temporary, you know that one. So I'm going to connect accordingly, yani negative to negative, positive to positive. See, so I'll connect like this. So I'll connecting this way. So connect it for a short time because you know that it will charge exponentially. Definitely it will take some time. And this time I don't have resistance. So it will quickly charge. And I think it is sufficiently charged. Now I remove it. After removing now, so this capacitor is now having charges, and again it is a temporary. If I keep it for a long duration of time, it will simply decay. Now I'll try to check whether it is charged or not. So how can I check? The way is that if I connect the load, yani this LED, it should glow. All right, but it will not glow for a long time. Like it is not a constant source. It is just a temporary, okay? And it will quickly decay now, okay? See, so I am going to connect again positive to positive, negative to negative, and I think you can see the LED now clearly, right? So I'm going to connect it. See this. Finish.
oh yes, it's glowing.
Oh yeah.
It's finished. See, if I touch it again, no, it will not charge. So if I charge it again, I can see this one again. So no problem, I'll do it again. So I put it on the battery for again some time. So it will charge maybe because it's very short time, you know, and we can, you know, reduce the discharging time if we have a resistance in the middle so that we can control again. Okay, let's see now again. So I'm going to connect it again. Bus finish. It will, you see. So some charges now 0. So it's completely discharged. So this is a capacitor basically, and how it works. It is a passive component which can store the energy. Clear to all? Okay.
Yes. Yes.
Yeah. So
Yes.
because you people are not having physical lab, if you visit it, so there are chances you can see the components. We have component like resistance in the lab. We have resistance, capacitance, inductance. If it is a temporary, then why do we use it, or in what we can use? Okay, good question. See, this is temporary storage. So, you know, the role of this one is not to give the supply. It's not a source, right? It's not a source. It is temporary. So temporary, the role you will understand later on. It is used in filtering application. Filtering yani when we convert AC into DC. You know the adapters. These adapters, mobile chargers, which you called, right? What it does basically, when I connect a USB port here, which voltage it will give me, AC or DC?
DC.
AC.
DC. No, it will give you DC. You connect AC here, all right, and you got it from here DC. It is 5 volt DC which you will be getting. Okay, so the point is this adapter is basically, even it could be your mobile adapter or laptop adapter. It converts this AC into DC, converting, right? So it is a AC to DC converter. So how does it do these things? So we need a capacitor. So over there, capacitor used as a filter to basically eliminate the AC component from there. Okay, yes. Inside there is a lot of, you will see a lot of components nowadays, because you know with that technology is gonna be shrink. But at that time capacitor is designed on the chip itself, IC. That's why the size is very small. This is a separate capacitor, but we have here a different type of, you know. So this is used for different purpose. It's not only, so maybe you are thinking it is a temporary battery is behaving like it. So we are not going to use this one as a temporary battery. We are going to use it for different applications. Like one of the application is wave shaping circuit. Maybe you will see in the slide. I don't remember what is the going to be next, but it should be there. Wave shaping circuit is what basically we have a sine wave. All right, and at that sine wave we want to clip some of the portion of it, some portion, maybe the positive half. You can use the capacitor to cut it. You can cut some of the negative also. So this is the use of it. There are a lot of use of the capacitor. Like if you just Google it, you will find the application of the capacitors. Then you will see. So we are not going to use as a battery, definitely, but this is one property that it can store the charge. So what I want to show, yes, it is stored the charge, and how can we see whether it is stored or not stored? So I connect a load there like LED, so that you people can see how whether it is providing source and supply or not. This is something clear to all of you.
Yes.
Yes. All right. There are a lot of things. Maybe inshallah digital hardware is the next course of advanced course of electronics. If you study that one, hopefully inshallah you will be having physical lab there. You will be able to perform experiments there. So there are a lot of ICs are there. You will see a lot of gates and all these things. So inshallah you will learn. All right. So let's continue this one. I am going to off my camera. Maybe then signal will be less. And now continue this one. So now this is about the discharging, girls. So for discharging, as I said, it is now the capacitor is connected here. So what are the things which I know from this circuit? We can quickly write it down. First of all, do we know initial voltage of the capacitor? Yes?
No.
No.
No, we don't.
No, it is given.
Where? Oh, okay. Yeah. 10.
Because, 10 volts. No, now it is charged. This is the different question. This is different question. What they are asking this time, they are saying we have a capacitor and it is holding this much of voltage. Clear? Initially, the switch is open. Open yani, it is not giving supply to this resistance. Circuit is not closed. It is not, current is not flowing. So it is keeping its charge itself until I am not going to close the switch. Is it clear?
Yes.
Okay, so it is initial things is given to me. This is the something which is given. All right, so quickly I can do one thing. At least I can calculate time constant, which is R10 raised to power plus 3 multiply by 2.2 10 raised to power -6. So just calculate this one first. It is
millisecond.
Yeah, I think 22 millisecond, correct?
Yes.
Yes.
Better to keep in millisecond because another time is also in millisecond. So we'll keep our calculation easy this way. All right. So what is given as I have given time which is 6 millisecond. So they are asking that in 6 millisecond how much it will discharge as I close the switch. This is the question. All right. Now, so we know that the equation V is equal to VF and what is there? V is equal to VF plus VI minus VF e raised to power minus T over tau. And now I can put the values VF, girls. Now, so when I close this switch, what will happen? The voltage which is 10 volts across the capacitor, finally, what it gonna be? It is gonna be 0 or not?
Yes. It will
Yes.
Because it will discharge, final value will be 0. So it is gonna be 0 plus final value, right? Initial value is 10, or just give it VI. So okay, better I will just rewrite this equation. Okay, but after putting this,
Doctor, are you sharing the screen because I can't see anything?
Really?
Yeah.
Girls, can you see this?
Yeah, it's appearing. I think you can pin it. Yeah. You should pin the screen.
Okay, so I can do one thing. Just stop sharing and then again sharing. See now? Visible?
Yeah.
Okay, so what I was writing, it has gone now. So no problem. So the equation which we were writing, it is gonna be V is equal to VI and what is that?
VF.
V 1 minus E raised to power minus T over, no, it is going to, okay, see, I think either I should write the full equation, then I can remember this is what VF, send plus, this is plus, not that this one, plus VI minus VF e raised to power minus T over RC. So what I put, this is both are 0. When both are 0, so equation will be this basically. Correct?
Yes.
Yes.
Okay, now put the value. Initial value 10, e raised to power minus T is given to me 6 millisecond. So it is gonna be what? 6 over, and RC we calculated 22. So this is gonna be V. Now got it.
7.61 volts.
7.61 volts. Yani the voltage which is now currently this capacitor is having 10 volts. As I close this switch, so after 6 milliseconds, what will happen? That voltage reduced to 7.61 volts. It means is that. All right. Now, if I ask you, girls, how much this capacitor will take to fully discharge as I close the switch?
5 to.
5 to, yeah. So fully discharge, huh? Fully discharge. So it is gonna be how much? 5 to. We know this rule. So 5 multiplied by 22, it is gonna be 110 millisecond. Means in 110 millisecond, this one is gonna be discharged. E is not. E is just exponential. It's not electron. It's exponential value E, because you know the curve is exponential. So it is that E. It's not electrons. Yeah, it's not charge. If it is electronic charge, we will use the value Q. Okay, it's just exponential value. Mathematics symbol E. Constant. It has value. So calculator you can use. Clear now? Understand these concepts?
Yes.
Yeah.
If I ask you draw the discharge curve, so you know the shape already. It is gonna be
Decrease.
yes, something like that. So here you can find some value. This is gonna be 110 microsecond. No, it is not shape. It is the rising exponential. Yani it is gonna be something exponential value right here. So this is what 110 millisecond, because it's a 5 to and something, but you can draw a few more values here. Initial value is 10 volts, something like that. So it is drawn already, and if it comes to draw, you can also draw this thing. So it's an interesting question, and 2 questions is more than sufficient to understand the complete concepts. This is something. Charging and discharging. And by the way, this circuit is called RC circuit. Why we call RC? Because we have resistance, we have the capacitor here. So RC circuit, we also call RC circuits. So next chapter is we will discuss RC. Now, yeah, any question? Yeah.
Can you please repeat how do we find when it is fully discharged?
Okay, so it's just 5 to 5 to required fully charged and fully discharged. See this one, it's mentioned here. If you see this universal curve, so you can see the blue one. So can you see this one when it is going to be 0 value?
Yes.
5 to. Similarly, charging maximum, same 5 to. So 5 to is basically the time required to charge and discharge, fully charge or fully discharge a capacitor. So if you know to, then you can simply find how much time it will take to fully charge and fully discharge. Clear?
Yes. Thank you.
Okay. Okay. Now, see, this question is a little bit different in the sense, rather than having a constant voltage source battery, we have a periodic pulse. And you know the periodic pulse means it is something like that. It will be high for a time, then it will be low, it will be high, then it will be low, because it's a periodic. It will keep on repeating. So what will happen, girls? So we are having here resistance and the capacitance. So what will happen? The capacitor will charge and discharge accordingly. Yani, during this charge, when the voltage is supplying, capacitor will charge. Now, after that, capacitor will discharge, because this means, let's suppose it is given 2.4 volt max. And what is the minimum? 0. So when the voltage is 0, so what will happen? What is supplied to the capacitor during this positive cycle? Okay, so this source is giving supply to the capacitor during positive cycle. All right, as the this becomes 0, yani this is 0 now. What will happen? The capacitor will return back the energy to the circuit in the opposite direction. Getting point? So it will charge during that time and it will discharge during when the signal is low, and it is keep on repeating. One cycle, second cycle, third cycle, and so on, something like that. Is it clear? Concept is clear? Okay, because it's this time we don't have a fixed voltage, we have a pulse train, okay, which is high low. So capacitor charge, discharge, capacitor charge, will discharge, like that. Now let's see what they are saying in this question. So they are saying calculate the voltage across the capacitor every 0.1 millisecond. We want to know how much is the voltage across a capacitor with every 0.1 millisecond. So here is a voltage source, okay, and we divided this one accordingly. So this is given to you that it in 1 millisecond it is completing its cycle, and we divide into 0.1, 0.1, 0.1, 0.1, yani 0.5. So it is divided like that. So they want to know, just draw the waveform and check every 0.1 millisecond how much capacitor will discharge. Yeah, very first thing is just calculate the tau, correct? So calculate the tau. We can easily calculate the tau first. So how much is the tau? RC. So 15 10 raised to power 3 multiplied by 0.0056 micro, yani 6. And better you just calculate again in milli, because 0.1 millisecond, 0.1 millisecond, like that. So you can do one thing, just multiply 15 by 0.0056 and you will be getting your answer in milli. Yes, so 0.084 millisecond. Yes, that's it. All right, now, so first of all, girls, it should be clear to you what will happen during this time. Capacitor will charge or discharge?
Will charge.
Charge. Okay. So do you remember the charging equation, which is V is equal to VF? Okay, maybe it is not clear to you.
Yeah, VF multiplied by 1 minus A.
Yes, 1 minus e raised to power minus T over tau. So this is the equation we will be using for the charging condition. All right. So you can say like at T is equal to 0.1 millisecond. What is the voltage? So what I will say, okay, it is 2.5 multiplied by 1 minus e raised to power minus 0.1 over 0.084. Okay, you will get something. Getting point? Second time. T is equal to 0.2 millisecond. Yani every 1 millisecond they said la. So I will change it and I will get it like that. Okay, then you will get it. Getting my point? How we need to calculate this? Correct?
Yes.
So every 1 millisecond we will calculate first for charging condition. So see, the solution is there already because writing too much not possible. So first case we calculate the RC, then we are going to consider the charging condition. So we will go this way. So this is something. So at 1 millisecond, equation is gonna be this way. Then 2 millisecond, then 3 millisecond, then 0.4 millisecond, then 0.5 millisecond. So this is what at 0.5 millisecond you can see how much it is charged. 2.49 volts. Correct? 2.49 volts. So this way we found that it is charged up to this one. Now guys, next step is what? And if you go back to the previous slide, you will see that it is 0.5. Yani during that time it will charge. Now at exactly 0.5, this value 2.5 is becoming 0. Yani this is the case where capacitor is gonna be discharged. So girls, exactly at this time, what capacitor is holding? It is holding the maximum value, which is how much? 2.5 volts. Okay, later on it is gonna be discharged from that value. So we will consider another equation of it, and with every 0.1 millisecond we keep on increasing the time and we keep on noting it. So very first thing now, so second equation, decreasing exponential, this is the equation. All right, now so at 0.6 millisecond we are saying 0.6. Why we are saying 0.6? Because here we want to know what happened here, so this is what 0.6 according to this one, but it is gonna be 1 millisecond for the discharging condition, because we know that capacitor is now fully charged at 0.5. After that it is gonna be discharged, so we will consider t 0.1, t 0.2, 3 and so on. But according to this graph, we want to know what happened at this instant, which is 0.6 here, here, like that. So don't confuse with what we are writing here. Yani here, see this one, what my point is. Yani this is what, this is according to this diagram. But what exactly value we need to put? 0.1 millisecond, another 0.2 millisecond, another 0.3 millisecond, after 0.4 millisecond, 0.5 millisecond. You can see, so after 1 millisecond this much voltage will remain, this much voltage will remain, this much voltage will remain, and finally it will be 0.01 volts will remain after 0.5 millisecond. So what we got charging and discharging, and now time to draw the graph. So this is the charging, you can see, so it will be charged something like that. So maximum is 2.5, now it will discharge. So this is something, charging and discharging. Clear concept, how to apply this approach and how to get it this one. All right guys. This is capacitive reactance, and the unit is same as the unit of resistance, yani ohm, because it is similar thing, any opposition to flow of current by the capacitor. This is AC circuit we are talking. Okay, this is called capacitive reactance. Now girls, so question would be like that: the reactance of this much of capacitor when a frequency of 15 kilohertz is applied. So just put the value of C and F, 2 pi, you will be getting the reactance. Okay, and reactance will be 226 ohm by putting this value. All right, this is capacitive reactance. Now girls, reactance, as I said, it is same as the resistance. So girls, when you are having capacitors in series, please watch carefully. When the capacitors are in series, the total reactance is the sum of the individual reactances. Yani, it is same as you add the resistances when they are in series. Remember, T is equal to R1 plus R2 plus R3, like that. But when the capacitors, the total capacitance you want to calculate in series, the formula is this one. Remember this also? Correct? So don't confuse with that. This is total capacitance when the capacitors are connected in series. And this is what? Total reactance when the capacitors are connected in series. Because as I said, capacitive reactance is similar to the resistance, and when resistance are connected in series, you know the formula. Is it clear to all of you?
Yes, it's clear.
All right. So this is, you need to relate the things with the previous. Now assume this much of capacitors are in series with this much of kilohertz AC source. What is the total reactance? So it's so simple. Either you calculate first reactance, okay, of 1 and then multiply by 3 because they said 3. All right. Or what is that? You calculate the total capacitance because they are 3 capacitance in what they are in series. So either you can use this formula, which one? Reciprocals of the sum, to get the first, this one, 1 over 1 over C1 plus 1 over C2 plus 1 over C3. After getting this one, you can say XCT, which is gonna be 1 over 2 pi FCT. Is it clear, this formula? One approach. And second approach, you just calculate C1 for any capacitance, yeah, right? Or just say C because it's just a single capacitance and all values are same. 1 over 2 pi FC, you will be getting here. After getting this C, what I will, sorry, it's not C, sorry. This is XC, huh? XC, yeah. So after getting this one, I can say XCT total, which is gonna be what? XC1, XC2, and XC3. Okay, by the way, C is in the suffix. Or you can say 3 XC. Clear? Because same. So whatever you feel it's okay for you, you can go this way. So you can calculate it. See the solution now, how they calculate. I believe they calculate first the XC simple, which is 1.93 kilo ohm. Now they are connected in series, so total reactance is gonna be just sum or multiply by 3, 1.93. Answer is 5.69 kilo. This one. Clear? 79 kilo. This is capacitive reactance. All right. Any doubt? Any question here?
No, it's clear.
Okay. So capacitive reactance is gonna be treated as resistance. Similarly, girls, capacitive reactance when capacitors are in parallel. So it is same formula which you use there. Reciprocals of the sum of the reciprocals, correct? Also, when two capacitors are connected, and now again with if the this much of capacitors from the last examples are placed in parallel with 2.5 kilohertz AC source, what is the total reactance? So how can we go for this? To approach again, which is the easiest one this time, you know? Can we calculate CT? They are in parallel. So when capacitors are in parallel, the formula of the total capacitance, remember girls?
Yes.
Yes.
So can I calculate this way?
Yes.
Correct. Now after that, XCT is equal to 1 over 2 pi FCT. Just quickly calculate this one. F is 2.5 10 raised to power 3 and CT is given 0.099 10 power minus 6. Kindly calculate it and check it. How much is there?
Uh, 643.05.
Okay, and it is gonna be what is the unit?
Ohm.
Ohm. All right. This is the answer. Okay. Now see how they are calculating here in this. So 643.05 and see this approach. So they calculate first XCT this way, right? This is the, because they already know XCT 1.93. So they just apply the formula, one of the reciprocal, that one. So it's up to you how you want to calculate. First calculate the capacitance or directly calculate this one, XCT. Hope you clear, you know, hope you have idea of what I want to explain in the previous examples. We have different approaches. So this is capacitive reactances, girls. Class now. So, okay, how many slides are remaining here? Let me just check. Still there are many. Okay, so we can, let's see, inshallah. So what I was explaining, this is capacitive reactance for the series which we done. Next one is for the parallel which we have discussed. Now see, this is the interesting thing here. So we can have a circuit where we have only capacitors, they are connected in series. So if you look here, it looks, you know, it resembles the one which we have discussed earlier, which I have drawn also here. Like if you remember this type of divider circuits we have discussed earlier, like this is R1, this is R2, right? So So now this is for the capacitive divider circuit, though it is a series divider circuit. So two capacitors in series are commonly used as a capacitive voltage divider. The capacitors split the output voltage in proportion to their reactances. How they split the voltage? In proportion to their reactance and inversely proportional to their capacitances. You know that this one also. So proportional to their reactances, girls, if I ask you how much is the V out? So the way is that either, do you remember if I ask you here V out in this case, what will you write? You always write V out is equal to R2 over R1 plus R2 multiplied by Vs, if this is Vs. Clear? Is it clear to all? You know this one, right? Now, same formula you can write for this capacitive reactance. How? This is, let's say, XC1. Let's suppose this is XC2. If we know, I don't have, if I know. So I can write the formula V out is equal to XC2 over XC1 plus XC2 multiplied by Vs. Did you get it?
Yes.
Understand this point? Yani, if I know the reactances formulas which you learned earlier, it is gonna be same. But if you wanna calculate with the capacitances, so formula is gonna be what? Not XC this time, C1 over, because what they said, yeah, C1 over C1 plus C2 multiplied by Vs. Like a current divider formula. Do you remember? Like a current divider. This is gonna be this way. So both will work. But which you wanna use it, you have to go accordingly. So now, sorry, this is not C1 plus C2, girls. It should be what it should be? CT. What was that? We have discussed this formula earlier. Just go back. Let me see this one. Yeah, maybe a little bit confusion. Series. Yes, this one. CT over CX into Vs. This is the formula. Voltage divider. So let me correct it. So if you wanna use the voltage divider, so one formula is this one. Just reach there now. Okay, this formula. Where is that question? This one here I was discussing. So this formula I can write simply CT over C2 multiplied by Vs. Is this like that? So both formulas will work, either this or this. You can use it. So which you wanna use, it's up to you. So let's see now the solution, how they are solving. So first of all, we need to know the XC1, yani reactances, if we wanna apply this formula, this one. Okay, I'm using red color now. So get it first XC1. Similarly, you need to get XC2. Okay, after getting XC1, XC2, we can apply the formula. We get it XC total first, which is 5.30, and then finally we can have this formula, which is similar to the resistive divider circuit formula, XC2 over XC total, which is 482 over 5.30, and we will be getting, this is 91 millivolts. So this is 1 volt. Here V out, we will be getting 91 millivolt or 0.019. Is it clear now? How to get this voltage here? By knowing the capacitive reactances. Okay, any question? And you can also apply another formula, Vs formula. Are you listening or not?
Yes,
Yes, we're with you, doctor.
Okay, I thought maybe everyone's silent now. So this is right. Okay, so we can go this way. If you want to apply another approach, you can see in this question. So another approach is also there. So in this question, again, similar question, what is the voltage across C2, right? So you can say this is a series circuit. They are asking C2. So girls, let's see with another approach, this one, okay? Where we know this formula, which is V2 is equal to C total over C2 over Vs. So here, you don't need XC total, you can directly see. Now, this is the point here, girls. Yani, how can you save your time? I am interested to know the voltage across C2. So if you go this way, you must know XC2, XC total. Then you have to calculate this one. But if you apply this formula, you need C total first. But by the way, these two capacitances are in series. And how to calculate the C total? Can you tell me the formula for C total when they are in series?
Yes, a 1 over 0.01.
No. This is the
okay.
point. Yeah, it is like opposite formula for the resistance. Do you? That one, product over sum, right? So this is the chain. That's why I said what I said. You just need some practice, then inshallah you will be able to get it. So you need to get it CT first, then you can apply second formula. So C total will be calculated this way, then you will be applying, and then you will get the answer. But if you apply first one, so you have to calculate XC1, XC2, then XC total is gonna be sum, because it is treated as the same as resistances. All right, so do some practice of maybe, because you people are having an examination, but before the next, inshallah, you will be just practice it, and you will know more about this thing. Now, capacitive phase shift, which is again very interesting. Like if we have a circuit and in which we are having a capacitor, so there is a property of a capacitor. What happens? See, when a sine wave is applied to a capacitor, sine wave, okay, so there is a phase shift. Yani, this is a property of a capacitor. When you apply a sine wave to it, it produces a phase shift in the voltage. So there is a phase shift between voltage and current, such that current always leads the voltage by 90. And this one can be asked in multiple choice question or somewhere. Very important point. So what is that? The current leads the voltage by 90. See, so if this is the voltage, girls, okay, across the capacitor, so current will lead yani start early, you know that, and touching the positive axis. So it is something, yani it is starting somewhere here advance. So this is a 90 phase shift. So if we just get this difference, this is the phi here. Okay, sometime, just to give you confusion or just checking your knowledge, can I say current is, current is always leads the voltage by 90. Can I say voltage is lags?
Yes, you can. Lags current by 90.
Clear? So we can read opposite also. Any voltage lags the current by 90. Okay, it's just to confuse sometime. So once one thing is clear to you, yani it is clear to you, current always leads by 90, leads the voltage by 90. So concept has to be clear. I can also ask in the reverse order. And same concept which you are learning for the capacitors, girls, it is gonna be opposite for the inductor, which is gonna be next chapter, inshallah. So just understand first, then we'll see what is next. Okay, then power in capacitor. So it is again interesting. Now, what is that? Energy is stored by the capacitor during a portion of AC cycle and returned to the source during another portion of the cycle. You know that. Yani once it is charging, it is consuming. Another half of the cycle, when it comes, it returns. So what? Voltage and current are always 90 out of phase. For this reason, no true power. This is important. No true power is dissipated by a capacitor, because in half cycle it is storing energy, in another half cycle is returning the energy, so it's not consuming the power. That's why we say no true power is dissipated by a capacitor, because stored energy is returned to the circuit. You know that one, right? So that's why no true power. So the rate at which the capacitor stores or return energy is called reactive power. The unit for reactive power is VAR. Which power capacitor store? It is called reactive power. Okay, energy. The rate at which capacitor store or return the energy is called reactive power. The unit of reactive power is VAR. This is also asked, important. Volts ampere reactive. And how do we calculate this one? You will see this one. So these are the formula, simple. To calculate the reactive power of the formula, you know that PR, VRMS, IRMS. PR, VRMS square over XC. So we will not use C, you know that. We will use reactive, like what is the equivalent in resistance? XC. This is the formula. PR, I square into RMS, XC. So this one will give you the power, and this is VAR, volt ampere reactive is the unit of the power. Maybe we have a question for that to understand this point. So determine the true power. If I ask you true power, girls, what should be your answer? Straightforward. True power, I just explained to you. Capacitor does not dissipate any power. So true power is always 0. Is it true or not? Correct? This is
Yes.
0.
Yes.
But it has reactive power. So for the reactive power, we can use any formula. Okay? So just use the reactive power formula. So true power is 0. And reactive power, we need to calculate XC. So here we need to spend some time to calculate XC all the time. Then PR, VRMS, because we have given already root mean square. And for the AC source, we always use VRMS. You know that one. So VRMS square over XC, and this way we'll get this one because of 10 power 6. So it is gonna be micro. So 503 micro VAR, and the unit is very important. It is not gonna be watt this time. It is VAR because of reactive power in capacitor. This is something new which you can highlight. Okay, so this is, I think we have done with that, and this is some key questions which you can go through, girls. And okay, if you want to see this one, okay, go through. The capacitor of a capacitance will be large if can you do yourself? Leave it. C. This is C, correct. Plates is increase. So area, because it's directly proportional to the area. Second, can you do this yourself so I can leave you, or just continue?
Yes, sure.
Okay, it's just simple. You can check yourself. There is nothing which is very difficult. So inshallah you can. So this way we have covered now. So inshallah. So but next week what will happen? Because this week you already lose one.